Hi, my name is Miloš and welcome to LM14's Robotics 101 Part 3. This time we're gonna make a robot arm. Let's go! Welcome to Part 3. In the last two parts we've covered electronics, mechanics, control engineering, but it's finally time to build something, and this time we're gonna make a robot arm. When I say robot arm, you probably think something like this. A bunch of joints, things like that. But we're gonna go much simpler so that anyone can follow along even if they don't have a 3D printer. So my idea with this is to make a SCARA robot arm, which will essentially be just two of these segments, as you will see later in the video. But first, let's generally discuss robot arms, what they are, and just some cool other different configurations. Let's talk about robot arms. So here on the left you can see a regular robot arm, and if you take a closer look, it's the same configuration as the orange robot arm I was just holding in my hands. By same configuration, I mean the same configuration of joints. Joints are here labeled in yellow. In red you can see the TCP or the tool center point, and we also have the segment lengths. If we have all of the segment lengths and all of the joints and their configuration, we can define the whole robot arm, and this is a simple block diagram of how that can look for a robot arm like this. Now, when we talk about robot arms, we're usually interested in kinematics. That means direct kinematics and inverse kinematics. Direct kinematics, we begin with the joint angle, so for all of the joints, and from there we calculate the coordinates of the actual TCP so that we know where our robot arm actually is, or the tool on that robot arm is. Vice versa with inverse kinematics, maybe we want to place the tool at a certain coordinate. To do that we need to calculate all of the angles in the joints, and that's the actual inverse kinematics calculation that you will see for the SCARA robot arm. Now, what is the SCARA robot arm? That is a completely different configuration, and you can see it here. So it's a planar robot arm where we have two joints that move the tool, and the tool just moves up and down. This is the block configuration for that. There's also, for example, the parallel robot arm that you can see here, and so on. There's a bunch of configurations, but these are just some of the more popular that you can more readily find in the industry. Let's continue with the project and look at the hardware for it. Before we get to making the robot arm, let's look at the hardware that we're gonna use to actually make it. First of all, we're gonna use the Raspberry Pi Pico 2W. It's a brand new microcontroller, it's more than powerful enough for this, and it's a small form factor. This is just a small perf board PCB I made, and you'll see the schematics rather soon. And besides that, we're gonna use servo motors. Now you may ask, why not use stepper motors or BLDC motors and so on? One thing, simplicity. This is the main goal of this course, is to keep it as simple as possible, so for people that are doing anything like this for the first time, they can get all of the basics and just understand how we translate theory into actual practical robotics. And for anything else, well, there's a bunch of other videos that you can see on LM14 Presents when it comes to robotics. So let's first take a look at the electronics and continue from there. The first thing we're gonna cover for this robot is the electronics, since it's so simple. As I already said, our robot is gonna have two joints and an actuator at the actual end effector, so it's gonna be really simple. We're gonna use a Raspberry Pi Pico since it's so powerful in such a cool small little form factor, but we're gonna use the second version just because they're pretty much the same cost as Pico 1. Besides that, we're gonna have a power connector for supplying the power to our servo motors, and the actual Pico will be powered through a USB cable. Two of the servos that we're gonna be using are gonna have analog feedback lines. This is just an additional line that will feed the Pico ADC, so we can measure the actual angle and get some graphs back when we're actually controlling the robot arm. And the third will be just the simple SG90 servo. So let's write some basic firmware for the Pico to actually test out the servo motors, and then go and make our robot arm. Here's the code for the Raspberry Pi Pico, and it's rather simple since all of the heavy lifting for the robot arm will be actually done on the computer. Pico is pretty much just our gateway to controlling the servo motors, so all it will be doing essentially is having an infinite while loop where it will listen for serial commands. How this is set up is for the commands to pretty much resemble GUI Code style commands, and if you take a look at, for example, G1 command, all you do is parse the string that's coming over serial and just check whether it starts with G1 or whichever other command, and then it's followed by parameters that are needed for that command that are separated by spaces, and you can see here the list of all of the commands. Also, if you're using any kind of different servos, for example, you can set it up here at the top of the code, whether that's the pinout, the maximum or minimum microseconds of the on-time in the PWM signal, and so on. So let's just see a small little example of how we can actually control a servo motor with this code, and then go and make the robot arm. So here on the bench we have the Pico 2W. I just wired up a few connectors for the servo motors and a connector for power. And here I attached a DF Robot servo motor with analog feedback. So let's test it out. Here is the serial monitor. Now when we, for example, send a question mark, we can get a list of all of the commands that the Pico can use. So for example, if we go M100, you can see some stats about the configuration and so on. Also, we can do some simple movements. So for example, if we type in G0A, for example, let's say 100, you can see that the robot arm is moving, or minus 100, you can see it's moving again, and so on. We just get an acknowledgement here that the command was okay. Generally, the command would require more parameters here for the other servo motors, but it just detects the first one, as you can see. So it works. I've just fed this later into Claude, and this is what I use to make the graphical user interface that you will see later in the video for the actual robot arm. Now that we have all of the basics covered, like the servo motor and firmware, it's time to get into actual robotics and direct and inverse kinematics. So we're gonna begin by sketching out a SCARA robot arm, doing some equations, and then see how we can translate the theory into actual practical robotics. Let's go more into depth into the SCARA robot arm. SCARA stands for Selective Compliance Articulated Robot Arm, and here is the drawing that you've already seen. So we need the two joint angles and we need the segment lengths L1 and L2. So we can figure out what's happening with TCP. We're gonna make this robot arm by using two servo motors, as I've already explained, and for the tool we're just gonna use a pen so that the robot arm can actually draw. So let's do some math and kinematics. It's not as bad as it looks, trust me. So this is the top-down view, if you can imagine, of this robot arm. We have those two segment lengths, we have the TCP, and we have joint 1 and joint 2. What we actually want to do with direct kinematics is going from joint 1 and joint 2, go to the TCP coordinates xt and yt. Both segments L1 and L2 will contribute to both x and the y coordinate. So let's begin with the x coordinate. Here I've noted those as L1x and L2x, and we have the angles Phi1 and Phi2. So Rxt is just L1x plus L2x, and L1x is rather simple, it's just L1 times cosine of Phi1, but it's not as simple as that for the other segment, and here you can see some of the math behind it. We actually need to find this small angle beta, and we can find it through the angle delta, as I've noted it down here, which is pretty simple because the sum of all of the angles in a triangle is 180 degrees, and we also have around J2 the 180 degrees, and that's how we get to the beta being just Phi2 minus Phi1, and that's how we get the xt coordinate. For the yt coordinate, it's pretty much the same, where we just go with sine. Now it's important to note here the actual sign of the Phi2, because we define the positive angle direction as counterclockwise, so anything that actually goes below, as Phi2 is now, will actually mean that the angle is negative, and that's why all of those values are like this, and this is our final calculation for the direct kinematics. Now for the inverse kinematics, we're gonna go backwards. For the inverse kinematics, we begin with the TCP coordinates, and we want to find out the angles of both joints, and this is probably the one that's more interesting to us, since if we want to position a robot arm to reach something or to actually draw something, we need to know how to configure both joints so that the actual tool reaches that point. So first we begin by defining this R, which is the distance between J1 and TCP, as you can see in the picture. Now, if we begin with the triangle that's made from the sides L1, L2 and R, and use the law of cosine, we can write this equation, and from there we can pretty easily figure out the angle phi2. It can be one of two values, and you'll see later why this is important. As for phi1, there are multiple ways we can find it. One of the easiest ways is to go with the same triangle and use the law of sine, and by that we can find this small angle alpha, which is part of this large triangle, and then we can get the angle phi1 as the sum of alpha and another small angle gamma, which is just the incline angle of the actual TCP point, which is just an arctan. So yeah, that would be it for inverse kinematics. It's not that bad for a SCARA robot arm with only 2 segments. And to go back to the 2 values that we can get for phi2, that is because you can imagine this going 2 directions, because the sign is important. It can go elbow up or elbow down, meaning we can reach the same point with 2 distinct configurations. This wouldn't be the case when the arm is completely stretched, where we would have a singularity position, where the only actual solution is for phi2 to be 0 degrees. We're in Fusion now, and we're gonna take a look at the CAD for this robot arm. So the first thing you can see, it's just 3 motors, as we've already talked about. So it's these 2 big servo motors and a smaller SG90 servo motor here. So how does all this come together? There are 2 bearings here just to make the whole assembly a bit more stable, but they're not strictly necessary. And also, if we take a look here, this is 150 millimeters, and also from here to here it's 300 millimeters. So both links are at 150 millimeters, which was my goal, so we can keep the math as easy as possible. I've also designed this weird mounting system here, just so I can mount to a clipboard I have, so that we can actually do some drawings with this SCARA robot arm. It might not look the same as you've seen in the actual drawings before, but the concept is pretty much the same. We have 2 motors in the same axis here, moving the end effector, which is our pen here, and this small here servo motor just moves the pen up and down with this little cam system inside. So that would be it for the CAD. You can find all of the CAD files, so both step files and STL files, on MN14 community. And now we're gonna go take a look at the graphical user interface for this robot and finally test it. We're in VS Code now, and we're gonna check the software for controlling the robot arm. You've previously seen the firmware, and these are the commands that you've already seen before. So this is just what I actually fed into Claude as an API reference, essentially, so that we can create a graphical user interface that communicates with the robot arm. Claude is really good with Python, so especially with PyQt, so this was really nice and easy to create. It just needed a bit of debugging, but in the background it uses pretty much the exact same math as we've already seen in the drawings, so that's the same thing. It just looks much nicer when you take a look at it like this. So this is the graphical user interface. You can send direct jog commands, for example, here, as you can see, with the arm moving, or you can send, for example, references to where you want the arm to move, and you can see that as I move to X or Y, it actually simulates how the robot arm should actually move, and we'll see how that actually works in practice. We also have a CSV path player, where we can load up a custom CSV with a bunch of, let's essentially say, points to which the robot arm should go, and we can trace different outlines. For actually generating those shapes, I'm also going to provide you with a Python notebook that has a bunch of codes for generating circles, squares, and many other shapes, so that you enter your dimensions, it generates your CSV shape in a bunch of dots, and when you load up that in the graphical user interface, your arm will actually replay that path. There's also this configuration JSON file, which essentially saves all of your calibration things. So for example, when you make the robot arm and you don't align the servos perfectly at 0, but it's a couple of degrees, you can jog the arm by each joint individually a few degrees and set that as a new home point so that it knows when the arm is completely straight, so that the inverse and direct kinematics are actually true to what you're gonna see in the real world. There's also this Python notebook with just some interesting simulations that you might like to see. For example, where the singularities are, so when the robot arm is completely straight out, it can reach that in only a single position, and that's called the singularity, and so on. So you'll have all of these codes for free, of course, as always, and let's go to testing. And the robot arm is complete. As you can see, it doesn't look really like the drawings itself, but that's the actual robot arm. And as you can see from the CAD, we have the two segments. Both of these segments are 150 millimeters to make the math easy, and you've seen the math seems to work. But now we're gonna finally test it out and see how that looks in practice and whether those equations make sense or not. Okay, now we have the arm fully built and it's connected, as you can see on the graphical user interface. So now when we click the home position, for example, you can see that it actually moves for the arm to be completely straight. And you can also see that here on the actual graphical user interface. So for example, if we try moving it like this, you can see that we are getting the movements that mimic what's also happening on the user interface. But of course, and if you take a look at these movements, you can see that the arm moves a lot, and that's the main issue with servos like this. They just aren't that accurate, and there's a lot of slop in them actually. But I mean, for the price and for the simplicity of how easy they are to use, they are a pretty good deal. And again, this is just a bit of a thing for learning, and you can see that for that it does the job really good. So as you can see, the robot arm completely mimics what we want to do, and these are just some manual jogs. And in the next tests, we're actually gonna do some inverse kinematics and following some trajectories. We've seen some simple jog movements, now it's time to see the inverse kinematics. So this is done with this panel here, and the pointer here that you can see on the graphical user interface, this is what our robot arm actually wants to reach. So if we go and say move to XY, you can see how it moves rapidly. So for example, if we put it like this and say move, you can see that the robot just goes to that position. This also means that we can do this, and so on. Now you can also imagine that if we, you can see the moves are rather nice. Now you can imagine if we've gotten a bunch of dots like that, we could actually trace some paths, actually do some drawings, and that's exactly what we're gonna do in the next test. We can also do live XY send, where as we move the coordinates slowly a bit, the robot arm will just start moving. As you can see here, we can also start the stream and look at the data as we move. And you can see how quickly we actually reach some of the references and things like that. So yeah, this is actually working rather nicely. And you can see that it had to change the move completely for it to reach it actually. Let's go somewhere where we have both angles, so the left and right angle for the first joint. So yeah, this works rather nicely. Let's look at how this actually draws something and follows some more complicated CSV paths. Okay, so we've seen some simple tests with jogging the joints. We've seen inverse kinematics. Some other things that you can see here are the setup calibration, where you can adjust a bunch of parameters that you've seen in the firmware code, and you can see the whole console and how it looks like. This is pretty much just the serial monitor. Now one thing that I want to show you is the CSV path planner. So here we can load up a custom CSV. So for example, let's load up, I've tried a bunch of shapes, let's load star 2. You can see that it should be looking like something like this. Let's do rapid move because that works much better. Click replan and let's click start playback. When I click start playback, the pen should go to the first point, the pen should go down, and it should actually draw out this shape. So let's see how that works out. Of course, you can also adjust the speed at which this goes, but this is some default speed where I managed to get some decent results without losing any detail. So maybe I'll just speed this up a bit so you can see the final result. And we're complete, and as you can see, it didn't actually lift up the pen, so let's do that manually. But as you can see, the star looks actually pretty nice. You can see that it jiggles a bit when it goes around. That's because it actually stops between each point, so it's not as accurate as it could be, but still the results are rather pretty good. You can do this much better, of course, with proper path planning, look forward algorithms that would make the actual paths for both the servo smooth, so you don't have any jagged edges in them, and so on. But my goal with this video was just to show you the basics of kinematics, inverse kinematics, how all of that goes, and for you to see that you can actually use all of that stuff to actually get results that actually look like something real in real life. So let's do another quick test. So that would be a star. Let's do, for example, the E14 logo. Let's go to the path planner. Let's go load CSV. It should be this one. Yes, let's click replan and let's click start playback. And that's complete as well. Let's do pen up and let's move the arm out of the way somewhere here. And as you can see, we have the E14 logo here. So yeah, it works really nicely. This was my whole goal with this, to make it as simple as possible, so just that we can see some connection between actual theory with all of those equations that you've seen in the beginning and with actual real world results. And that's literally it. You've seen the math, you've seen how we actually convert both angles into coordinates and vice versa through direct and inverse kinematics. And these are the results. We can actually do all kinds of different paths. And of course, we can go much further with this, as I've mentioned before, with a bunch of proper algorithms for look forward, for actual path planning. But we already got some really cool results. Thanks so much for watching part 3 of the 1114's Robotics 101. I hope you had fun, and we finally made our first small robot. As you've seen, all of that theory actually makes sense now, and we can translate it into practical projects, and it's really not complicated for a robot arm like this. Even for robot arms like this, there are build solvers, and I'm gonna roll a clip now to see how that, even for something like this, you can also make it easily. Try going down. While it's still jittery, you can see that the robot arm is going perfectly up and down. Now if we try going just along the x-axis, which is this, which is the front of the D-pad, you can see how it's trying to hold that position until it reaches the singularity for that. And also if we go back, you can see it will try doing that. If you try going much more further back, it will actually fail because the base can't turn by 180 degrees, and it also works if we go to one or the other side. So you can see how it goes in a straight line, and if we go to the other side, this part of the movement is rather smooth, and that's because the inverse kinematics are rather nice even without any path planning. But for example, for the z-axis, if we go, there are some moments when it's kind of jittery, like there, for example. But yeah, you can see that it's all working now, even in real life. So the only thing left to do now is combine the test between the robot arm and the platform itself. If you wish to check out that project, you can check it down below in the description. It's also on Element 14 Presents. As always, all of the files, all of the code, and everything that you need to actually recreate this project will be available on Element 14 community. If you have any questions or comments, please leave them down below. And in the next part, we're gonna tackle mobile robotics. Until next time, see ya!